Right, let's start. So last time we briefly discussed about the graph clustering, in particular spectral clustering, right? And yeah, there are a few other clustering methods that are quite popular. So the first one is this affinity propagation. So that is also graph clustering method, which doesn't necessarily require the feature vector representation, but requires just a graph representation. I mean the similarity between the particular pairs of the data items. Okay, and yeah, this affinity propagation was quite popular at some point. And so yeah, it also provides the open source, and I believe the scikit-learn library will also provide this affinity propagation as one of the available clustering methods. And also another one is called the Markov clustering. Yeah, so this is also another graph based clustering method. And so this is quite simple, but it was used to quite popular as well. And also we already looked at this deep cluster method. Okay, so that's it for the clustering, and the next topic that we discuss is dimension reduction. So yeah, usually our data is quite high dimensional vectors. So in the case of an image, if we have a 3x3 pixels, and then we can think of this image as a 9-dimensional feature vector. And also in the case of a term document matrix, our dimension is amounting to the number of the vocabulary size, or the unique keywords defined in our vocabulary. And so in the case of dimension reduction, so here let's use this kind of notation where our data matrix has the rows as dimensions and the columns as our data items. Okay. Okay, so it's some part of the animated slides, but yeah, given these high dimensional vectors, so 100 by 80, and then 100 features and 80 data items we have. And then in the case of dimension reduction, and this 100 is reduced to maybe 10, for example, and the number of data items will still be the same. So for each data item, we reduce their original dimension of 100 into a 10-dimensional representation. And so this dimension reduction has several benefits. So yeah, definitely less storage is required to store this reduced amount of data rather than this original data. And also faster computation. I mean, when using these vectors as an input to any particular algorithm, and rather than using 100-dimensional vectors, and 10-dimensional vectors will be much faster. In the case of, for example, in the case of a Euclidean distance computation, so computing the Euclidean distances will be proportional to, I mean, the amount of computation will be proportional to the number of dimensions. So and also dimension reduction plays a role of removing the noise, or discarding the irrelevant information to our task. And so often it works as a good pre-processing step for better accuracy or performance of our task. And also in the case of neural nets, if we have a four nodes in originally in the input feature vectors, and then if it reduces to maybe 3-dimensional vectors, then it is basically an example of dimension reduction, of representing originally 4-dimensional vector into 3. Okay, so when visualizing them, or when reducing the dimensionality into 2 or 3, and then we can utilize this dimension reduction into the means or the tool for visualizing the high dimensional data. So this TensorFlow embedding projector is one example of visualizing high dimensional data using dimension reduction methods. So it is reducing the dimensionality of a word embedding vectors. But let's use this MNIST data. Okay. Then it basically performs a PCA, and it's a three-dimensional result, but basically this is a two-dimensional dimension reduction result, and also each point is assigned a two-dimensional coordinates. And then let's see. Oh yeah, right. There was an option to represent it as just a single point for individual data items rather than showing the actual images over here. Okay, so their two-dimensional coordinates are determined by the dimension reduction method, and this MNIST data has the original dimension of 784, right? So 784 dimensional vectors are respectively reduced into the two-dimensional vectors, and their coordinates are determined in this manner. And let's see. So if we encode each point's the color of each point as its labels. So here label is corresponding to the digit that each handwritten digit image correspond to, right? So I don't know how to pan it, but but it roughly shows some segregation or separation between different clusters, right? So this is an example of PCA, but also we can use some other. Oh wow, I didn't know it also integrated another dimension reduction method called the UMAP. So that is another recent and popular dimension reduction method. So PCA is the oldest one and the most traditional one, and TSNE is another popular dimension reduction method, and UMAP is another recent one that is more and more used in these days. So if we perform the PCA, and then it takes some time. And so the first step is to find the nearest neighbors in this TSNE. And then it takes some time, so let me just run it over here. Why do we not have an internet? Let me try. Okay, okay. So it's by default running the PCA, so I cannot stop here. Okay. And also the iPad finished its nearest neighbor computation, and then runs the TSNE optimization over here, and unlike the PCA, which finds out the global, the final result as a closed form solution. Okay, through the eigen decomposition. But this TSNE is basically gradient descent based iterative optimization method. So yeah, it runs these different iterations. So these are the intermediate results during our iterations. So yeah, once running this TSNE on the MNIST data, and then yeah, we obtain some two-dimensional mapping like this, and their colors indicate different digits. So we can see that the TSNE is showing well separated clusters with respect to their true labels. So this TSNE result. Yeah, the point. Yeah, here. One notes that. Yeah, we didn't use any label information of each data, whether it is belonging to the first digit or second digit and so on. But yeah, TSNE result is showing quite well clustered result with respect to the true or ground truth labels. Okay, so that is another beauty of this TSNE. But anyways, so in this manner, we can utilize this this dimension reduction to visualize our high dimensional data. So, did I show this figure? No? So, yeah, this is this visualization example of when using the publication data. Yeah, papers, research papers published in various fields. And so here, I mean, the exact process is not the same, but let me briefly describe how this is obtained. So for each subfield of applied science and applied physics and electrochemistry and statistical physics and so on, so we can divide each academic discipline in this manner, and then it will have several list of journals corresponding to this area, and then we can collect all these papers published in this field, and then for each field we can represent each field as this bag of words representation like this. So this is an applied physics, and this is a maybe statistical physics and so on, right? And then once obtaining this feature vector representation of each field, and then we can reduce the dimensionality into maybe 2. So in that case, we can obtain this kind of visualization. And so here we do not know where it is, but we can imagine it's corresponding x and y axis, and each of these field is represented as a two-dimensional vector after performing the dimension reduction, and then this two-dimensional vector is corresponding to this x coordinates and this y coordinates. Okay, so that's how we obtain this kind of result. And so here the main idea of this dimension reduction is that we want to preserve the relationship between the data items in the original high dimensional space into the low dimensional space. Okay, so here in this bag of words representation, suppose this maybe chemistry, and this is maybe polymers. So these two have a lot of keywords in common in terms of their highly occurring or frequently occurring keywords. Okay, so in that case, those two vector representations in terms of which keywords are frequently occurring between these two fields, they will have a similar patterns, and thus their cosine similarity and also Euclidean distances will be quite similar, or Euclidean distances will be low, cosine similarity will be high, or inner product similarity will be high as well. And so if we have 100 different fields or 100 different data items, and then we can think of their 100 by 100 pairwise inner product matrix, right? So maybe inner product matrix or Euclidean distance matrix or whatever similar pairwise similarity matrix. Okay, so let's call this as S and high. So that is corresponding to the similarity matrix in the high dimensional or original dimensional space. Okay, and then also, yeah, this is almost like how this multi-dimensional scaling works. But yeah, let's assign this first data item as the new two-dimensional coordinates and the second one as the another two-dimensional coordinate. Okay, and then let's imagine we randomly initialize those two-dimensional coordinates for each data item, and then we can also compute this pairwise similarity matrix, right? So that is corresponding to the pairwise similarity matrix in the low dimensional space, right? And so we want to minimize the gap between them or difference between them. So this is the main idea of how this dimension reduction works. Okay, so we want to recover or reconstruct this given pairwise similarity matrix in the low dimensional space. Okay, so this low dimensional space and their similarity, suppose this similarity was represented as a Euclidean distance. Okay, Euclidean distance, and then in this case, the Euclidean distance in the low dimensional space is actually what we actually feel or what we actually see in this 2D embedding. So, for example, applied physics is located here, and electrochemistry is located over here, and their distance is not that far, right? So we can imagine that, assuming that this distance is quite close to high dimensional distance of their high dimensional vector representations, and then we can see that, okay, these two data items are quite close to each other in the high dimensional space, right? So that way, yeah, we can see that the applied physics and the electrochemistry, statistical physics, physical chemistry, and organic chemistry, and analytical chemistry, and pharmaceutical research, and so on, and polymer over here, and those are kind of close to each other, or they have a lot of words in common that occurs frequently. But on the other side, so we can see this language and brain studies and cognitive science and sports medicine and neurology and tourism and so on, and geography, and those are forming kind of roughly a single kind of one cluster, and these are quite far apart from these areas, and thus we can kind of make sense that those areas will not have much overlaps in terms of the frequently appearing keywords. Okay, so this is how we kind of can get the overview of our data. Okay, so in this manner we can kind of understand the relationship of our data, all at once through this visualization. Okay, so there are two different techniques for dimension reduction. The first one is a feature selection and extraction, and we already studied about this feature selection. So that is like as an output of this dimension reduction result. So feature selection is basically select 10 optimal features out of 100 features. So it means 90 features will be just thrown away. Okay, so that is a feature selection, and how we perform this feature selection can be done based on various criteria, like a forward selection and the backward elimination and so on. So those kind of greedy method, we studied about these greedy methods as well. And then now the next one is called the feature extraction. So feature extraction is each reduced dimension involves in general all the original dimensions. So here it's maybe height and the weight and so on, and then the first dimension is formulated as maybe weight minus height plus 100. So in this case it's degree of overweightedness, right? So suppose this guy is the definition of the first dimension. So definitely this first dimension is involving multiple original dimensions. And similarly, the second dimension is represented as maybe weight times height minus weight, for example. Yeah. So it has its own representations that involves multiple original dimensions. Okay. So this feature extraction, yeah, is involving in general multiple original dimensions or coordinates to form each of reduced dimensionality. Okay, and in general, most of the dimension reduction methods are falling into this category. And yeah, we discussed about this feature selection. So now let's move to feature extraction. So we have, yeah, there are tons of different feature extraction or dimension reduction methods. And they have different characteristics, but there are 4 different axes or perspectives that we can categorize a particular dimension reduction methods, whether they are linear or nonlinear, unsupervised, supervised, or global or local, or feature vectors, or similarity as an input to run the dimension reduction method. And in the case of a linear dimension reduction method, each reduced dimensionality, so it is like x1, x2, x3, is reduced into y1 and y2. So each 3-dimensional feature vector is reduced into 2-dimensional vector, and each of our reduced dimension or output dimension is represented as a linear combination of input or original high-dimensional features. Okay, so if one method falls into this category, and then it is called linear dimension reduction method. Okay. And there are other nonlinear methods as well. And in the case of a unsupervised versus a supervised dimension reduction method, so if we just take the high dimensional vector representation as just a single input, and then performing the dimension reduction, and then it is called the unsupervised dimension reduction method. But in the case of supervised dimension reduction method, as you will imagine, each data item has associated labels. So they are corresponding to maybe digit 1 and digit 2 and 3 and so on. So we give this class label information in addition to high dimensional feature vector representation. So if the dimension reduction method requires this additional input and utilize this information in a particular manner, and then it is called a supervised dimension reduction method. Okay, and then global versus local, I will explain it as we discuss in detail about multi-dimensional scaling very soon. And also, another perspective is, whether it takes feature vector representation or similarity representation. So, in the case of clustering, K-means is taking the feature vector representation and graph-based clustering method, such as spectral clustering and maybe affinity propagation. So they are taking the similarity matrix as an input to perform the clustering. So dimension reduction is almost the same. So in the case of dimension reduction, you can take this original feature vector representation, but it also takes the similarity matrix as an input. So in this case, we do not need or require the original feature vector representation at all, right? So in this case, it is not really reducing the original dimension. So it just generating. It just generates some multi-dimensional vector representation given this similarity input. Okay, so in that sense, rather than calling it as a dimension reduction, it is sometimes it's all composed of nice animation in the PowerPoint version, but it is called this graph embedding as well. So this embedding, Okay, this embedding, yeah, you can think of this embedding as a method to generate or gives an output as the some fixed dimensional vector representation of the data items. So if you are familiar with the word embedding, and then words are are not originally assigned a particular high dimensional vector representation, but out of some relationship between words, we generate a particular dimensional or fixed dimensional vector representation of words, right? So in that sense, we are embedding those words into a particular dimensional vector space, or we generate multidimensional vector representation of data items, right? And then what is the word embedding the input data? So the input data is like this kind of input and output word pair. So I study math very hard. Yeah, so in this case, we just put I and study. So we basically choose any two words, and then form this input and output. And then it means this I and study have some sort of similarity because they co-occurred in the same sentence, right? So for example, maybe dog, a dog, study, okay? Study. And in this case, we will probably not see, or it will be difficult to see this kind of sentence where dog and study are co-occurring together, right? So that means dog and study have a less similarity between them, right? So in that sense, if we just collect all these pairs captured in the same sentence and then forming our training data to run this word embedding neural net models, and then it can be viewed as like those data items or individual words didn't originally have any vector representation, but we are assigning the vector representation in a given dimensional space, right? And also, if you are familiar with another word embedding technique called a glove, in the case of glove, see. 글로브가 어디 있을까요? Right, yeah. So in the case of a glove, which is another popular word embedding method, the input is basically co-occurrence matrix. So we can think of these word by word, and if the two words are co-occurring in the same sentence, and then we just add their count, okay, in the corresponding position. So the first word is I, and maybe the third word is maybe study. So given our document corpus, we check each sentence, and for any given pairs of words we found in a single sentence, and then we basically count their number of co-occurrences. So that way we can obtain this co-occurrence matrix, which is viewed as a similarity matrix between words, right? So this is basically an input to the glove word embedding. Okay, so that is this PIJ. And then here, so this PIJ is the number of, you can think of it as the number of co-occurrence of the word I and word J. And UI, so UI is I's words vector representation. So if we have a maybe two-dimensional representation, I mean the target dimension is 2, and then maybe I is represented as a two-dimensional vector, and the study is represented as the two-dimensional vector, and this is a UI, and this is VJ. But you can, let's just make them equal to each other. So UJ, for example, and then here, this guy is basically the inner product in a two-dimensional space between the word I and the word study. Okay, so this inner product should be the same as, or as close as possible to, this log of pi. So log of pij is, pij again is like the number of co-occurrences, right? And then taking the log of it is something like this, right? So as we get more and more co-occurrences, number of co-occurrences gets larger, and then their rate, I mean increasing rate, is kind of attenuated, right? So that's the effect of this log function. So we are kind of transforming, this similarity matrix by taking the log of each values, okay? So that way we form another transformed original similarity matrix, and then we want to fit this matrix by using this inner product similarity, okay? So we want to fit this embedded vector and their inner product to encode as much as possible the given similarity, which is represented as a log of co-occurrence. So that is the main idea of this globe word embedding. Any questions? So in that sense, this word embedding or globe can also be viewed as a particular dimension reduction method that doesn't necessarily take the input as a feature, original high dimensional feature vector representation. Okay, and then now let's move to an individual dimension reduction method. The first one is the principal component analysis. Yeah, so this principal component analysis is heavily involving linear algebra, in particular eigen decomposition and singular value decomposition. But I'm not gonna go in detail and go deeply into this topic because it will take a lot of time. But I'm gonna give you some high-level kind of meaning or understanding of this principal component analysis from the perspective of this multidimensional scaling. Okay. So as you can see, this multidimensional scaling is really a big category of dimension reduction method or graph embedding method. And then in particular, this classical MDS or classical multidimensional scaling is basically PCA. So PCA is one kind of multidimensional scaling, and multidimensional scaling is it works as follows. So this is almost similar to this kind of setting. So let's imagine given 100 data items, and let's suppose their dimensionality is maybe 500. So we originally have 500 dimensional vectors, and then 100 different data items, and then we can compute their Euclidean, pairwise Euclidean distance, right? And then let's call that as TH, okay? And then suppose we want to reduce the dimensionality into 2, and then as I mentioned, so let's just randomly initialize the two-dimensional vector representation of each data item for each of the 100 data items, okay? And then we can compute their corresponding low-dimensional pairwise distance matrix, okay? So here this xi is just a two-dimensional representation of i's data item, and the two-dimensional representation of j's data item, and this is the norm operator, right? And this Euclidean distance in a two-dimensional space should be as close as possible to the given. Yeah, this is a high-dimensional pairwise distance between the data item I and j. Okay, so this is like this dh, and maybe I comma j's component over here. Okay, so that is our delta I comma j. So that is our ground truth or target distance value that we want to fit. Okay, then yeah, because it involves this this involves maybe the square root, and so to just make it convenient, and then let's consider this a squared difference. I mean the Euclidean distance squared and this guy squared instead of using squared over here. Okay, so in this case, I suppose we have maybe 2 comma 1 as i's point, and maybe 3 comma 4 as j's point. Okay, so in this case, yeah, we can easily compute their Euclidean distance 1 and 3 and square root 10, or their squared distance is 10, right? So current distance is, I mean, the squared distance, so the current 2D embedding is 10, but let's say their ground truth or ideal distance is maybe 7. Okay, so in this case, this distance should be shorter or smaller to fit this ground truth value, right? And in this case, let's just apply the gradient descent algorithm to update those two elements. So x1, y1, maybe x1, x2, and y1, y2. So this is a first data item, this is a second data item, or this is an xi and this is an xj, right? And then x1, y1 squared, x2 minus y2 squared, right? And minus 7, yeah, 7, right? So this is our loss function, right? And then we can easily compute the partial gradient with respect to x1. So what is the current value? So it is 2, 1, and this guy is currently 3, 4. Okay, so in this case, it is easy to compute the gradient. So it is, yeah, so this is our loss function, and dx1 dl is that's it, right? dx2 is and that's it. Right? So in this case, let's apply this x1 and y1, so 2 minus 3. So in this case, -1 or -1 times 2, right? So in particular, in proportional to this value, we have our gradient imposed into x1. Okay. Oh, you. So, yeah, I was wrong. So, yeah, instead of removing this guy, so we have, yeah, we need maybe absolute value, because that is our loss value, the difference. Or, I mean, there are many different forms, but yeah, let's imagine like the squared difference between the low dimensional distance squared and the high dimensional distance squared. Okay. Okay, let's, for example, imagine this kind of loss function. Okay, and then we have the squared over here, right? So that is more natural. So sorry, but let me rewrite it. Right. And then yeah, we can just compute this gradient and x1 minus y1. Right? And then for x2, yeah, we do the same thing. Oh yeah, and over here we have 2 as well coming from here. Yeah, and x2 minus y2 times 2. Okay. Okay, and so currently this guy is 10, right? So 10 minus 7. Okay, and then so it's also 10 minus 7, and then x1 is 2, y1 is 3. So 2 minus 3 over here. So that is the partial gradient with respect to x1, right? So we have this positive value, and with respect to x1, this y1, or the second point, or yeah, let's imagine, so you are this point, okay, you are this point, and we have to update their x coordinate, right, which is an x1. Okay, so this is another point that that we consider the distance of, right? So its distance is currently 10, but it is it is ideally 7. So it should be like, yeah, intuitively the distance should be closer. So this guy should be going to this direction, right? This direction, right? And so this part is I mean, the gradient is proportional to the difference between the low and the high dimensional distance. So if it is yeah, ideal distance is 10, 7, and then our current distance is 10, and then we have 3 over here. But if we have maybe 12, and then this value is 5, right? So this gradient will be proportional to the difference between the low and the high dimensional distance, right? And then also we have 2 over here, and then this is an the gradient along the x direction, and this is the gradient along the y direction. So it is x2 is 1 and minus 4. Okay, so so altogether it's positive and negative, right? And then we perform gradient descent. So we take the negative sign over here when adding the some amounts to the original value of an x1, right? So original x1 new is this x1 old minus some step size, and this guy, and 2 minus 3 and 2, and the x2 new right? Okay, so this part will all be the same, and this part, yeah, is together with the negative sign over here. Okay, negative sign over here. Then 2 minus 3 is this vector. No, 2 minus 3 is this vector, right? But we have a negative sign over here, right? And so we have this vector, 3 minus 2, and 1 minus 4, and its negation is like this vector, right? So this is a gradient corresponding to the x direction, and this is the gradient to the y direction. So the point is, this point is updated along this direction, directly pointing to this point. So yeah, intuitively that direction is the most efficient direction that will reduce the distance gap, or this discrepancy in our distance. So we have a distance of 10, but ideally it should be 7, and so the distance should be closer, and so the gradient will be like, gradient will be generated directly towards that other point. Okay. So you can think of it as like some spring force. So we have ideally 10, but ideally 7, and it's 10. So we have maybe this amount of a discrepancy. So our force or gradient will be proportional to this value, okay? And also the direction will be pointing to this other point. But if ideal distance is 7, but our current distance is 5, for example. In this case, this one will not only give us some amount in terms of their absolute value, but it will change this the direction of this gradient. So in this case, this point will be pushed away directly, away from this point. Okay. So this is a simple example of how this gradient descent is performed to obtain or compute this multidimensional scaling. Okay. So in this manner, this point, for this point, we have many other things to consider, because out of maybe 100 data items, this is the point itself. We have other than itself, we have 99 different points. So this is one of them, and we have other 99 points as well. And so we consider their ideal distance and the current distance, and then for each of them we will generate the partial gradient with respect to the x-axis and the y-axis. And then we have like a total kind of gradient or aggregated gradient in terms of the x-axis and the y-axis by considering all the pairwise distances with respect to 99 other points. Okay. Right. That is Yeah, like this representation, and this is called the metric MDS. And are there any other method than this metric MDS? And that is called this non-metric MDS. This non-metric MDS is that. So here we kind of make this multidimensional scaling more flexible in a way that, yeah, in the case of a metric MDS or the original MDS, we need this ground truth, yeah, information about this pairwise distance itself. So we need the detailed information about the distance value itself between any pair of our data items, right? But what if we have this kind of relationship where maybe data item 1 yeah, let's say, yeah, we want to embed maybe apple, orange, and banana, okay? And then let's think of the distance of an apple and orange. And yeah, we don't know, yeah, we cannot easily define the exact distance between apple and orange, but we at least know, or we agree that the distance between apple and orange is less than apple and banana, or less than orange and banana, yeah, by considering their shape, okay? So yeah, banana seem to be quite far from orange and apple, but between orange and apple, they seem to be quite close, right? So in this case, yeah, we can think of this kind of pairwise, I mean relative ordering of these distances, okay? So in this case, instead of, yeah, defining, yeah, each exact value corresponding to each element in this matrix, we just consider, okay, this element is smaller than this element, and also this element is larger than this element, and so on, okay? So we can take the input as this relative distance kind of inequality or ordering in terms of their distances, okay? So if we have this relative ordering or this kind of inequality as the original input to run or perform this MDS, so that is called this non-metric MDS, okay? Because our distances are not computed from this metric space of the original high-dimensional space, okay? So in this case, it is called the non-metric MDS, but yeah, so we only care about this ordering of this distance, okay? And then here, yeah, we will not discuss the full details of the algorithm for this non-metric MDS, but at a high level, we know this guy is smaller than this guy, okay? But compared to this guy, is larger than that guy, okay? So we have this kind of, yeah, set of inequality form of a constraint. And then, yeah, let's randomly initialize those two-dimensional vector representation for each data item. And then let's consider their low-dimensional pairwise distance matrix. And then let's, yeah, let's consider their corresponding elements over here. Okay, so these are the corresponding elements to those three. Okay. So in this case, suppose this guy is, the distance is 3, and this guy's distance has the 4. And does it satisfy our constraint or inequality given over here? So it satisfies the inequality, right? Because this 3 is smaller than 4, right? So in this inequality, yeah, we are completely okay. But let's say it is 5 over here. So here we violate this kind of inequality, right? Because this guy is greater than this guy, so that is our constraint or that is our inequality that we gave to run this algorithm. But currently, so 5 and 3 is definitely violating this constraint or inequality, right? So we only identify those pairs. Okay, only identify those pairs that violates our given inequality. Okay, and then now in order to perform the gradient descent, or maybe differentiating some loss function, we need some quantifiable or some measurable or quantitative definition of our gradient, of our objective function. So here, this clearly violates our constraint, but how can we represent the quantity of a violation? So in this case, simply we can represent this guy as the number of the amount of a violation. Okay. So yeah, in this case, if it is a 1, and then this guy becomes 1, and then it's the case of no violation, right? It satisfies this inequality, right? So this one is not exactly true, not fully correct, but only considering those are violated case, and then we can just define the difference and their squared values as the amount of a violation, right? And so in this case, we can define our loss function in this case. And so in this case, the rest of the story will be the same. So we suppose this one is the first data item, and this one is maybe fourth data item, and then we update the first and the fourth data item and their low dimensional coordinates, so that this one becomes smaller. So it is a little bit tricky to determine our loss function, so this one shouldn't be our loss function, right? So our loss function should be, let's fully define our loss function. 3 minus 5, or maybe 5 minus 3, and 0 max. So you guys know the hinge loss, right? Hinge loss. So suppose this guy is a second data item, it's a fourth, and maybe it's a third data item. And so our loss is like, this part is represented as the low distance and the x1 and x2 minus the low x4 and x3, right? So this is placed over here, right? Okay, so this 5 is over here, and 3 is over here, right? And then we know this guy should be bigger than this guy. So that is our initial constraint as an input to run this dimension reduction, right? So we just take the difference between the potentially lower one, from the lower one to the, subtract this potentially larger one to the lower one. So in this case, if it is a greater than 0, and then that's the amount of our violation, right? And if it is a smaller than 0, and then our loss becomes 0, because we completely satisfied our constraint in the form of this inequality, right? And then we update, we can just consider, given each of our inequality, and then we can define our loss function as this sum of these hinge loss. Okay, it's the sum of this hinge loss, and then take the partial gradient, partial derivative with respect to each variable, and if the loss is 0, and then in that case, yeah, it will give us zero gradient for the involved variable. Yep, and if it is a non-zero loss, and then that will involve this x1, x2, x4, and x3 and their low-dimensional coordinates, and then yeah, and then we can accordingly update their their coordinates. Okay. Although I will not, I didn't give full details or full examples, but hopefully you get the idea. Any questions? 이해가죠? So once updating at a particular iteration or particular step of our gradient, iterative gradient descent, and then we form this low-dimensional low-dimensional pairwise distance matrix, and then we check whether each of our inequality has been satisfied or not. Okay, and then some of them might have been satisfied. For example, after one step of an updating, then this guy became maybe 4.5, and this guy became 4.8, for example. In this case, we satisfied this kind of inequality, right? But here, sometimes during our updating or our iteration, some of these constraints may have been already satisfied, but in the later iterations, then it may not be satisfied. In the later iterations. So in this case, while updating the coordinates of this guy, and then this pairwise distance has been increased, and so it is now larger than this 4, but this guy should be bigger than this guy, right? So in this case, this constraint between these two has been previously satisfied, but during our updating, this guy is no longer be satisfied, right? So for this guy, we will generate our loss function as non-zero value, and then from that loss term, we compute their gradient, and then update the corresponding point. So in that case, not only this point gets updated, but also this point will also get updated as well. So 1 and maybe 6. So anyways, this is a high-level overview or sketch of how this non-metric MDS works. Okay, so there is no real magic even in this non-metric MDS, as long as we define quantitatively the amount of a violation of our inequality as this kind of hinge loss or whatever suitable loss function. Okay, then back to this principal component analysis. So how is it related to multidimensional scaling? So in the case of a PCA, so you guys know PCA is finding out this major axis according to the maximum variance that our data has. So given our two-dimensional data represented in this form, so this one is the first major axis, and this one is second major axis. So eigendecomposition on this covariance matrix of our data item, and then it will give us this particular direction. Okay, so the first direction is corresponding aligned with the maximum variance direction, and the second direction is the second largest variance direction of our data. Okay, and then in the case of PCA, it performs the orthogonal projection. Okay, orthogonal projection. So for this, usually this PC1 and PC2 is represented as a orthonormal basis vector. So suppose this axis is maybe 3/5 and 4/5, So this is one example of a unit vector that has the length of 1. Okay, so in this case, if we have this point, and then the first dimensional coordinate is computed as this orthogonal projection and its length along this direction, right? So suppose this one is 3,6, and then this length is computed as the inner product with this unit vector that indicates the direction of the first principal component, and then this guy, right? So this is the length of this line segment, right? And that is yeah, so this is because, yeah, so here this is theta, right? And then we have this length, right? Let's suppose that length is on A, and then this part or this line segment is obtained as A times cosine theta, right? And then in this case, so suppose this guy is vector A, and then it can be represented in this form. And then this vector is represented as maybe V, okay? And then this guy is A dot V A dot V divided by, so A dot V is like this guy. So this is the definition of the cosine, the inner product. And then we want to obtain this part, and so we have to divide it by the norm of V, but by definition we already used the normalized vector V, which has the length of 1, right? So this is 1, right? And so okay, so right? So this is the line segment, or the length of this line segment, and then it can be represented by using the inner product between the two vectors A and V, and then A and V are represented in this form. And so in order to obtain only this part, we have to divide it by the length of V, or the norm of V. And so the inner product divided by the norm of V, but this norm is 1, and so this part, this line segment, is simply obtained as this inner product between A and V. So this guy is that inner product, right? And then also, yeah, so this is the first coordinate, first dimensional coordinate, and the second dimensional coordinate will be like, so we have a second principal component which also has some unit vector having some particular direction, and usually this direction is orthogonal to each other, right? So those two vectors are orthogonal to each other, and so yeah, I mean the projection of this point onto this line is also similarly obtained through this inner product between this guy and that guy, right? Okay, so that's how we compute this PCA once obtaining this directional, unit vector corresponding to the first principal component and the second principal component, and then simply performing this inner product will give us this reduced dimensional representation. But here, yes. So here, why is it a linear dimension reduction method? So let's say this one is A and this one is B, and say this one is x1 and x2, for example, and then the first dimension or the first target dimension or the first reduced dimension is represented as ax1 plus bx2, or the linear combination of the original input feature x1 and x2, right? So performing the inner product to obtain this orthogonal projection. Okay, so inner product is basically the linear combination of the original feature. Okay, so that way this PCA is falls into the category of linear dimension reduction method. And theoretically, if we use this orthogonal axis or orthogonal directions as a projection axis, and then using these orthogonal axes, and then optimizing this kind of criteria that we studied in the context of an MDS. So in this original high dimensional representation, we can consider their DH, and then suppose we choose suppose this one is three-dimensional vector. So originally three-dimensional vector and their corresponding high dimensional pairwise distance matrix, and then let's consider their two-dimensional dimension reduction result, but we only allow the linear transformation to obtain each of our reduced dimensions. Okay, and then also those linear the projection direction should be orthogonal to each other. So if we obey or follow this kind of constraint, and then dH and dL, and then dH minus dL, and then Frobenius norm, and we want to minimize it, and then suppose two of our axes as W1 and W2, which are kind of unit vector and orthogonal to each other. So in this case, so these two vectors are the solution for this minimization problem is obtained as the two largest eigenvectors from this covariance matrix eigen decomposition result. I mean, this is kind of a theory that kind of from the perspective of an MDS, we want to minimize this Euclidean distance and their differences, right, for all the pairs of data items. But if we allow our dimension reduction as a linear dimension reduction method, which can be represented as this projection onto some vectors, okay, some directional vectors, and then if we only allow our dimension reduction as this linear dimension reduction, and then the optimal solution for this W1 and W2, that will produce so W1 transpose, which is like some particular dimensional vector, and then some input vector x, and then that way we obtain our first dimensional coordinate in the reduced dimensionality, and then by using W2, using the same input vector, and then that will produce the second coordinate, right? So in that sense, W1, W2 transpose. So this is our linear transformation matrix, right? So in this case, our Y is defined as W transpose X, and X is a three-dimensional vector, and W transpose is like 2 by 3 vector that will produce two-dimensional vector. So here our constraint over here is that those two vectors are having the unit norm or the length of one, and then their vectors are orthogonal to each other, right? So rows are orthonormal in W transpose. Okay. Okay, so if we follow this kind of constraint, and then the optimal solution that will minimize the squared differences of all the pairwise distances between high and the low dimensional space. So the optimal solution is obtained from eigen decomposition. Okay, so that is kind of a high-level story about this principal component analysis is actually viewed as the multi-dimensional scale. Okay. Any questions? Okay, then let's take the 10-minute breaks and then resume at the 4:58. Yeah. 네.
과제 때문에
네.
그 평가 기준을 좀 여쭤보고 싶은 게 저희가 자유주제를 하고 있는데
네.
이제 실험을 하다 보면
네.
최종적으로 원하는 결과가 안 나올 수도 있잖아요.
네.
그걸 왜 안 나온 것 같다라고 잘
네.
분석을 해서 내도 되는지를
네. 그래도 그것도 가능합니다.
아 그것도
네.
아니면 아싸리 좀 적당히
바꾸시는
나오면서 쉬운 걸로 해야 되는 게 더 나을지를 모르겠어서
네.
네.
뭐 이제 실패 원인에 대해서도 뭐 어느 정도의 유의미한 분석을 했다면 그것도 뭐 괜찮습니다. 네.
네. 아 그리고
네.
기간을 한 이틀만 더 늘려주실 수 있을까요?
원래 저희가
주-
기간이 언제까지였죠?
다음 주 일요일까지인데
일요일이요?
다음 주에 시험이 많이 있어가지고
다음 주에 시험 있어요? 벌써?
네, 다 땡겨져가지고
그래요?
그러다 보니까 좀 한 이틀만 있어도 괜찮을 것 같긴 한데
네.
아 물론 맞추려고 노력은 하는데요.
네네. 뭐 연장할 수 있을 것 같습니다.
긍정적으로 검토해
네.
주십시오.
네. 알겠습니다. 네. 네. 그래서 주에 월요일 날.
17일.
네.
그리고 16일 전까지 없으시죠?
그 프로젝트요. 이거를 좀 지금 연장을 좀 요청하시는 분이 계셔서
그럼 주로
연장을 해도 될 것 같습니다. 네.
나중에 알려주세요.
네.
다른 거 자료 찾아보다가 고차원 데이터 리그레이션을 해보고
네.
그 디스턴스 기반의 매트릭보다는
네.
다이렉셔널 그런 코사인 시뷸럴티 이런 걸 쓰는 게 좋다고 나와 있는데
네.
그 이유로서
네.
고차원 데이터는 대부분 그 하이퍼스피어의
네.
그
네.
표면에 있다고
네.
데이터 설명했거든요.
네.
표면에 있다는 건 뭐 대충은 이해하겠는데
네.
그렇게 표면의 데이터 그렇게 고차원의 데이터 분포에 있으면 왜 거리 기반보다는 이 각도 기반이 더 좋은지 그 부분이 좀 제가 잘
잘 모르겠는데
네.
일단은 이제 하이퍼스피어에 있는 것은 그 하여튼 뭐 대략적으로는 그 뭐 각각을 뭐 각 디멘전al 값을 이제 랜덤 베리어 그 각각 인디펜던트한 랜덤 베리어블로 볼 때
네.
그럴 때 이제 인디펜던트 할 때는 그것들의 이제 뭐 하여튼 걔네들의 베리언스나 이런 게 다 베리언스의 합이 좀 약간 일정하게 항상 뭐 좀 나오는 뭐 좀 그런 것 때문에 하이퍼스피어에 좀 위치를 한다라고 볼 수가 있고요.
네네네.
그 다음엔 거기서는 거리를 따지면 글쎄요 이게 네거티브도 있는 건가요?
네네 있는 거 같아요.
네.
노멀라이즈가 일단 가정하고
나도 잘은 모르겠지만
네.
이게
네네.
또 뭐 약간 뭐 이런 거 있잖아요.
네네. 텍스트 인베딩 매트릭스의
네.
센싱레이트 구하는 이유 이런 거를 보통 그렇게 설명을 하고 있었는데
네.
매칭이 잘 안 돼요. 저는.
이게 잘 모르겠네요 나도.
잘
모르겠네요.
제가 아마 잘 모르겠습니다.
잘 모르겠네요. 네. Right, let's continue. Okay. And then, so at a high level, PCA can be viewed as a optimal solution for minimizing the discrepancy in the pairwise distance. So we want to fit the pairwise distances as much as possible. So that's the optimal solution when using the linear transformation, using the orthonormal basis vectors that will be obtained from the eigen decomposition and their solutions. And then yeah, let's move to another one called the Salmon mapping, and also the category of multidimensional scaling. So this is a local version of an MDS. So yeah, suppose our ground truth distance is, for example, 10, and maybe the ground truth distance is, yes, for some other pairs, the ground truth distance is on just 2. Okay, so in this case, so yeah, among many different pairwise distances that we have to fit, yeah, this MDS criteria will tend to fit large distances, yeah, more carefully. So in that sense, so suppose our original distance was 10, and then maybe it was yeah, this is DL, and this is D high, and suppose the original distance was 2, and then 2.4. Okay, so in this case, if we compute our loss function, then here we have a 4, yeah, as the difference, right? And here 0.4 as our difference. Let me change it as 2.8. So it is 0.8, right? So so which one is giving more errors, contributing to our loss function? Definitely this guy, right? Because that is 4 and this guy is 0.8, right? So in this particular situation, our model will tend to fit or tend to focus on minimizing the difference between these two rather than these two, right? And here, if we view their kind of relative distance error, so given the original distance of 10, and then it is giving the error of 40%, okay, with respect to the original distance value. And also this guy is also, if we think of the relative error with respect to the original distance value, it is still 40%, right? So in this sense of relative distance, their errors will be the same, right? So the Salmon mapping is actually having, yeah, so this is a delta ij, which we see over here, okay? And also this guy, yeah, this guy is a high dimensional distance, and this is the low dimensional distance, okay? And then instead of just using the squared sum of the difference, the absolute difference of these two distance measure in the high and the low dimensional space, we actually normalize it by its original high dimensional distance, okay? So in this case, it has the effect of focusing more on preserving the small distance, okay? Preserving the small distance originally. So what's the effect of it? So back to this figure. Right. So here, yeah, the main intuition behind this salmon mapping is that, yeah, it is more important to preserve this local relationship rather than this global relationship. So suppose the distance between this guy and that guy is around 10, okay? And then, yeah, putting this point over here or over here or over here and so on, yeah, and their errors will be like, yeah, ideal distance should be 10, but it is maybe 7 or 13 or maybe 12 and so on, and their error will be maybe 3 and 3 and 2 and so on. So yeah, we will not care too much on like preserving these really large relationship, I mean large distance or kind of small similarity value, right? But when using this distance measure itself as the values to fit in terms of their kind of absolute errors in this manner, and then it will tend to focus on preserving the large distances or small similarity relationships, right? Because we are using the distances as a measure to fit, right? And so in this case, yeah, we want to focus on relatively more on the small distance components or small distance pairs or high similarity pairs. So that way we have this normalization component over here. So that is the salmon mapping. And yeah, we can easily obtain, I mean, we can derive their gradient descent, right? In this case. So yeah, so the overall effect of this guy, yeah, is fitting or focusing more on preserving the small distances. So you will have much less errors within this local regions. Okay, so for example, applied physics is closer to this electrochemistry than to physical chemistry. So these kind of relationship may not be much distorted when using this salmon mapping. Okay, but in the case of original MDS, this local relationship may be easily distorted. Okay, so that is the notion of this locality of the dimension reduction method. So this falls into the category of this local dimension reduction method. Yeah, focusing on the large distance or the, yeah, and that is called the global method. And also, yeah, another multi-dimensional scaling example for a particular dimension reduction method is called the force-directed graph layout. So yeah, the main kind of characteristic or advantage of this force-directed layout is the interactivity. Right, so here, yeah, we can move this guy in this form. Right, so this kind of interactivity is provided in this force-directed graph layout, and this is almost the same as multi-dimensional scaling, but also it has additional kind of criteria or force where, I mean, yeah, it basically has this kind of almost, I mean, the criteria almost similar to MDS, but also this force-directed graph layout has additional kind of criteria, which works as follows. So, for example, this point, yeah, you see, if I try to overlap this point with some other points, it will kind of avoid, or it will just yeah, run away from that point, right? So that is due to additional kind of loss function corresponding to the repulsive force. So if for any given pair of points, if the distances are too low, I mean the distances are too low purely in the low dimensional space, and then we just put additional force that pulls them apart from from each other. Okay, so why is it useful? Yeah, I mean the main idea of using this kind of additional force is because, I mean, yeah, in general, if we see many kind of occlusion, in case we have a number of data points, and then suppose many points are overlapping with each other, okay, and in that case, it means in terms of a visualization, we cannot see the individual point properly, right? Because some of them are hidden, due to the other overlapping points, right? So in that case, clearly the visualization, that kind of visualization may not be ideal or desirable. So in order to consider this kind of aspect, we have an additional kind of repulsive force or its corresponding objective criteria, or our loss function as well. So we have this repulsive force, so it's almost the same as multidimensional scaling. Then the next topic is a linear discriminant analysis. So we studied about this in the context of a generative model and multi-class classification example. But this linear discriminant analysis is also used for the dimension reduction, and as the name says, it is basically a linear dimension reduction method, which forms each reduced dimension as the linear combination of the original dimensional value. And in the case of PCA, the objective function is basically try to minimize this low and high dimensional, discrepancy between the high and the low dimensional distances, right? So we minimize this to be able to maximally preserve the relationship in the high dimensional space, right? So that was our criteria. But in the case of a linear discriminant analysis, it actually has the completely different objective function as well, and that is it tries to kind of maximize the separability between the classes. Okay, so it falls into the supervised dimension reduction method. So in the case of supervised dimension reduction method, we have this additional label information as an additional input to this high dimensional feature vector, right? And so in the case of LDA, or linear discriminant analysis, rather than preserving all the pairwise distances as much as possible, it just tries to maximize the separability between the clusters or classes based on our given label information. Okay, so in that case, it performs these two tasks simultaneously. So the first one is putting the different clusters as far as possible. So more exactly, it first computes the centroid of each clusters in the low dimensional space, and then we maximize the distance between the centroid between the different clusters or different classes, because we are given the predetermined labels corresponding to each individual data items. And then also within each cluster, it tries to make each class or those data items belonging to the single classes as compact as possible. So that can be done by minimizing the distance between this guy and its centroid. Okay, so we put those points as close as possible towards the centroid. Okay, so this kind of process is done based on linear transformation. Okay, so we have a particular direction where we perform the orthogonal projection onto this axis, right? So we find out this optimal axis. Okay, so that optimal axis is also obtained through something called the generalized eigen decomposition. but there are a certain method based on some linear algebraic techniques that can find out this optimal axis. Okay, so that will give us this kind of representation. So this is some synthetic example that I generated in a 1,000-dimensional space as a 7 Gaussian mixture model. Okay, so I just set randomly some particular 1,000-dimensional vectors as a centroid for each different Gaussian component, and then we can set our prior as maybe as a uniform distribution as a 1/7 for each Gaussian component, and then we can maybe set our covariance matrix as some identity matrix. Okay, so we can simply set our generative model in that manner, and then I generated several data following this, and then their class labels are determined by its corresponding Gaussian component, ranging from the first to 7th Gaussian component. And then when running PCA, and then this one will give us this result, and you can see this result as those result that minimizes the discrepancy between the pairwise distances between high and the low dimensional space. But if we perform the LDA, then it gives this nice separation between the clusters. So in this sense, roughly the yellow point is located over here, right? And so what is the corresponding centroid in the low dimensional space? It will be somewhere around here, right? And then maybe pink point is represented over here, and then the centroid for the pink point will be somewhere over here, right? So we can think of their distance as this guy, right? And so we can compute each different pairwise distances between every pairs of our classes. So we have 7 classes, and so 7 times 6 divided by 2, 21 different distances between different pairs or clusters, right? And so we can maybe take the average of these differences between the 2 different centroids. Okay, so that is called the between cluster distance. Okay, so between different cluster we compute the distance by using their centroid, and so that is called the between cluster centroid, between cluster distance. And also we can consider the within cluster distance, and that within cluster distance is basically this guy. Each point and its distance to its corresponding centroid, or the Gaussian components and its centroid. Okay, so we can also compute the average of this distance of each individual point to its corresponding centroid of that Gaussian component. Okay, and then in this case, the distance, I mean between cluster distance is something like this. And what is the within cluster distance? I mean, the name of this guy is called the within cluster distance. And what is the average within cluster distance? And that is like given this point. So that is the centroid of a yellow point, right? And then we can compute all the distances of this yellow point to its centroid. Okay, so in this sense, in the case of this result, for each centroid is over here, and then between cluster distance is something like this. This guy, and this guy, and this guy, and that guy, and this guy, and so on. So we have 21 different pairs, right? So we take the average of these between cluster distances, and then this one is clearly larger than the right one, PCA one. And also, what about the within cluster distance? So those were those distance, right? And also those distance. So these are much smaller then the within cluster distance is over here, right? So PCA will minimize the within cluster distance, at the same time maximize the between cluster distance, okay? And in particular, or in more detail, this LDA is actually maximizing the ratio between like within cluster distance and between cluster distance, okay? So it will maximize this ratio. So that is like criteria of LDA. But this kind of criteria, you can design a different criteria. Like we want to, for example, maximize, and then this dB is maximized, and at the same time dW is minimized, or within cluster distance should be minimized. And then if we maximize this representation, then yeah, it will roughly performing the same thing, right? So it will maximize this guy and minimize this guy. And at the same time, when combining these two different criteria, we can utilize, or we can introduce some hyperparameters that will determine the balance between these two components, right? So this is an alternative method that will simultaneously consider these two aspects. But in particular, in the case of an LDA, they will maximize the ratio between the two. So that way the numerator will get maximized, but at the same time, the denominator will be minimized. Okay, so that is also obtained. I mean, optimal solution for that is also obtained as a generalized eigen decomposition. Okay, so we covered PCA, MDS, and LDA. And now let's move to a little bit more advanced one. And now the next thing is the manifold learning. Manifold learning. So let's think of the pixel space. For example, let's consider maybe just 3x2 image and grayscale image, for example. And we have 6 different pixels. And so like they are represented as a 6-dimensional feature vector, right? And then suppose our data is a collection of facial images. So in the case of facial images, they have their own kind of constraint, or they have their own statistics. So for example, okay, so and suppose this one belongs to the hair pixel, okay, and then the next pixel is likely to be also hair pixel, right? So in that sense, those two pixels will be quite close to each other in terms of their pixel values. So if it is really like facial images, and then it will be really unlikely to observe the image that has maybe this guy is a pure black and this guy is pure white. So in this case, it will not look like a realistic face or realistic hair part of our image, right? And in the extreme, so let's just randomly generate some images where each pixel is independently sampled from some Gaussian distribution or uniform distribution, and it will be just a mixture of like black and white and gray pixels, right? It's just a random mixture of these pixels, right? So in this case, similar to this guy, so if it is a really like a physically existing kind of existing kind of material, yeah, existing in our real world, and then the pixel values between these two adjacent positions, I mean, they will have some kind of constraint. I mean, although we cannot explicitly write down that kind of constraint, but those pixel values will not have really large differences, right? But here in this case, yeah, we can have, yeah, they are independently samples, right? Sampled, and so in this case, this image may also exist in also this pixel space, in maybe 6-dimensional space, but that pixel or that 6-dimensional vector will not belong to this region of facial images, right? So that way, our facial images as a collection of real face images, and then those points will occupy only some part of regions or some sub-regions out of this 6-dimensional space, right? So facial images, and then yeah, just drawing or yeah, maybe putting each facial images and its corresponding 6-dimensional vectors as a point, and then those points will never fill out the entire 6-dimensional space, right? So in other words, our real data of a facial images will occupy only some sub-regions out of this entire 6-dimensional space. Okay, so those sub-regions of our sub-regions that our data occupies, so that is called the manifold. Okay, that is called the manifold. And then this manifold has some some degree of freedom that will actually change our facial images. So for example, this suppose our facial images has this kind of shape in terms of their actually occupying sub-regions, and then we can roughly see that okay, these facial images have kind of differences or the variations in the progress of this kind of direction. As we move along this direction, facial images have some smooth changes, right? And then also we can see kind of this kind of direction, right? Along that direction, those facial images are relatively densely kind of placed, and so yeah, we can imagine kind of that direction may correspond to some meaningful kind of aspect or attributes to make the variations of our data semantically. Yeah, so it's a little bit, it's a little bit ambiguous, but we will see more detailed example. So, in the case of manifold learning, so what's the meaning of learning the manifold? Okay. So, this some meaningful variations, and they're kind of not necessarily linear axis. So here, so along this curved lines, there exists maybe some one particular attributes that will make this kind of changes, and another attributes that will make another kind of smooth changes, right? And then let's whether they are curved or not, let's map each of these axes or each of these attributes that will make this real changes in our data into each of our reduced dimensionality. So the first dimension and the second dimension, and then because once mapping into the reduced dimension space, our axis is always straight, right? If it is 2 dimensions, and then we can imagine this straight axis in our 2-dimensional space, and if it is 3 dimensions space in our reduced dimensional space, and then each axis will always be straight. So we can kind of view this kind of process of manifold learning as mapping this potentially curved kind of structure in our manifold into a straight line as one of our reduced axes. Okay. And then if this guy was actually a person's facial expression, starting from really frowning and no expression and maybe smiling, and that will be one of our meaningful axes that will make this kind of smooth changes in our data. Okay, so mapping this kind of structure, and then straightening up. Okay, straightening up every curved or every kind of potentially curved axis into each of our straight axis in the reduced dimensional space. That is called the manifold learning. Right, and in order to perform this manifold learning, so we utilize the following assumption that at each local region is approximately like linear, or at least that region is like a little bit straightforward, or straight or flat, okay, without any curvature, okay, when considering each small patches. Okay, so that is the main kind of assumption that we utilize to obtain this or perform this manifold learning. Right, and then let's see how we can utilize this local patches in order to learn this manifold learning. So the first one is called the isomap. I think I mentioned briefly about this isomap. Yep, so how can we map this curved structure into one of our straight axes, whether it is an x and y axis? And so we actually apply kind of similar idea to multi-dimensional scaling. So here, those 2 points in a pixel space, so pixel space and their points differences is computed directly based on the pixel vector, right? So this is a 1, 1, 1, 2, and 1, 3, and 2, 1, 2, 2, 2, 3. I mean, so this is the result of like this guy, and putting it into a straight or long and thin column vectors, and then we just imagine computing the Euclidean distance between the two facial images. Okay, so in that case, the distance will be computed as the line segment between these two, right? But here, if we imagine this kind of manifold structure, so this point, this part is the region where there exists no images. So no images exist. So along kind of this direction, we shouldn't compute their distances along that direction, following the route where there exists no real face images. Okay, so here we can consider the distance between the two as like, so this is really frowning, and maybe this is really smiling. Okay, and so this one is almost frowning, and then maybe no expression and a little bit small smiling, and over here a little bit clearly smiling. Okay, so in that case it may make sense to compute the distance between these two following our manifold structure, or following the route where there exists some non-trivial amount of data exists. Okay, so between these 2 points, we want to compute the distance between them following our manifold structure. Okay, and then how can we approximately compute these distance along this manifold structure? And that is based on forming the k-nearest neighbor graph of our data points. and that's where this local patches are playing their own role. So here, yeah, let's form the given this pixel space, let's form the k-nearest neighbor graph, which means based on the Euclidean distance for this guy, yeah, we consider, I mean, based on their just plain or original Euclidean distances in this pixel space, let's connect this point with this maybe k nearest neighbors. For example, suppose k is 5, and then maybe this image and that image and this image. By the way, each data point is our image represented in the pixel space, right? And so maybe this guy is the fourth closest one and the fifth closest one. Okay, we can form these edges between this single point and its 5 nearest neighbors with respect to the Euclidean, based on the Euclidean distance. Okay, and then for this point, we can also think of their k nearest neighbors and form or assigns the edges between this point and its k nearest neighbors, right? And then yeah, we can imagine like this kind of graph, right? Although many edges are overlapping with each other, but this point is having the edges of with its 5 nearest neighbors, and the other point may have this point as also a neighbors, and in that case it will have its own edges as well. Okay, and then once computing or once forming this k nearest neighbor graph, and then in order to compute the distance between this point and that point, yeah, we basically compute the shortest path along this graph. Okay, starting from this point and arriving at this point. Okay, in this case, we just follow the shortest path along this graph. Okay, right, and then that shortest path, or the sum of these edgy ways or edgy distances, on the shortest path, and that distance, the sum of these edgy lengths along our shortest path in this graph. Okay, and that distance can be viewed as an approximate distance along this manifold. Okay, right. So we compute all the pairwise distances based on this first forming the k nearest neighbor graph, and then computing all pairs shortest path. Okay, and then we can form this something like DH, which is a all pairwise distance matrix, but each element, and that is kind of that is viewed as an approximate distance along the manifold, right? So ideally, we can think of this a smooth line, okay, that can correspond to like this kind of blue line, right? But here, due to this approximation using k nearest neighbors, we just compute that distance approximately based on the sum of this shortest path. Okay, and then we compute for any pairs, for this guy and maybe that guy, what's the shortest path. Okay, we compute the shortest path and then their distance, and then that will fill out each element in our pairwise distance matrix. Okay, and then the next step is exactly the same as PCA or the MDS. Okay, so given this pairwise distance matrix, we form their low dimensional representation that will minimize the difference between DL and DH. Okay, and then for here, so we have to reconstruct this geodesic distance by using the Euclidean distance in our low dimensional space, right? So in that case, we will, the corresponding low dimensional axis is like the first text, it's like, the straightening up this kind of curved manifold into like really straight, straight surface, right? So in that case, our Euclidean distance in this low dimensional space will be almost the same, or approximately, I mean, as close as possible to the distance along this manifold in the pixel space. Okay, so that way we kind of mapped this curved axis into one of this straight axis in our reduced dimensional space. Okay, so that is called the isomap. And in the case of minimizing this high dimensional and the low dimensional space, right? And in this case, there are two different ways. The first one is following the gradient descent based on kind of this kind of formula, and then we randomly initialize their coordinates and do the gradient descent. But also, if we just assume kind of this kind of linear mapping, and then we can just utilize this eigendecomposition to just conveniently optimize the or conveniently compute the optimal solution for this that minimizes this low and high dimensional pairwise distances, right? And so here, in the case of isomap, once computing this DH by following our manifold in an approximate manner, and then we apply this PCA kind of algorithm to compute the optimal solution that will minimize the difference between this low and high dimensional distances. Okay, so that way we perform this eigendecomposition on this kind of matrix. Okay, so that's how we perform this isomap. Any questions? Yeah, and by the way, the distance following this manifold structure, like this kind of blue line, so that is called the geodesic distance. Okay, geodesic distance. So here, this kind of dashed line or dotted line is not geodesic distance because that is not considering our manifold structure. Right, so that is isomap, and it has been used quite widely. In when performing this dimension reduction, and there are tons of other manifold learning methods. And in general, this isomap and this manifold learning method is called the nonlinear dimension reduction method, right? Because our nonlinear structure is mapped into each of our axes, right? And also there are many different methods, and for example, locally linear embedding. Although in practice it doesn't work very well in different perspectives, but locally linear embedding was also quite popular. And oops. So it has tons of citation, right? 13,000. So that was locally linear embedding, and it was published in Science. Science. And then it was also published in different venues with almost the same algorithm. And that, I wanted to show the title of that paper. Think globally fit. Maybe it might be the other one. Like this one. Yeah, think globally and fit locally. And yeah, I think this one is this locally linear embedding, and it's NIPS version. Yeah, instead of science version. Yeah. So no, not NIPS, but I think it was published in ICML, and as you might know, ICML is all published in this journal called the Journal of Machine Learning Research, JMLR. So it's called a journal binding between the conference and the journal. So for a particular conference, all the papers accepted and published in conferences are included or published in the it's a kind of sister journal. So I think it was published in the ICML. No, it's not ICML format. Maybe it was published directly to the JMLR. Anyways, so this is on the locally linear embedding paper. Yeah, and I thought title looks quite cool because think look globally and fit locally. So yeah, so that is another popular manifold learning paper. And yeah, let me give a high-level overview of this locally linear embedding. So here, locally linear embedding is performed in this manner. So we consider the local patch, or the local patch by using the local patch, we are basically using the k nearest neighbors. So suppose this point, and then suppose we consider maybe 10 nearest neighbors around here, and then given these 10-dimensional vectors, suppose they are 3-dimensional vectors, and then maybe this is maybe 100-dimensional vectors. And then 100-dimensional vectors are given 10 different 100-dimensional vectors, right? And then using them, we have a center vector. This guy has also another 100-dimensional vectors, right? And then now let's try to minimize this least squares problem. Okay, and then what are these vectors? So these vectors are the best linear combination coefficient associated with the 10 nearest neighbor point, okay, to reconstruct or to represent the given point at the center, right? So for each data item, we perform this least squares problem, and then for each of them, if we set k as 10, and then we have 10-dimensional kind of linear combination coefficient that is brought from here, right? And so this is a first data items 10-dimensional representation with respect to is first nearest neighbor, second nearest neighbor, and 10th nearest neighbor, right? So that is best approximation and their linear combination coefficient, right? And then suppose we have maybe 100 different data items, okay, but dimension was 100, so let's say we have 500 data points, and then for each of them we consider its own 10 nearest neighbor, and then we form this kind of matrix for each data point, and that point is over here, placed over here, and then we just compute this least squares problem for 500 different representations, right? And then we will obtain this 10 by 500 matrix, right? So this value is like to reconstruct the first data item and its first nearest neighbor point and then its associated coefficient to reconstruct the first data item, right? Does it make sense? 이해가죠 이거? 이해가요? 네, 그러니까 이게 리스퀘어를 풀어서 이제 만약 500개 이제 데이터가 이제 100디멘전에 있으면 뭐 하나하나를 여기 위치시키고요. 그다음에 걔에 대한 이제 10개의 네이버를 여기에 다 위치를 시키는 거예요. 이게 첫 번째 네이버, 두 번째 네이버, 10번째 네이버. 그럼 여기랑 여기가 정해지니까 우리는 얘를 이제 리스퀘어로 풀 수가 있죠. 그러니까 주어진 센터 포인트를 가장 잘 나타내는 이 나머지 주변의 10개를 가지고 과연 얘네들의 리니어 컨비네이션을 나타냈을 때 이 가운데 있는 얘 중심이 되는 얘 포인트를 가장 잘 나타내는 그 개수 값을 찾은 거예요. 그럼 이거를 여기에다가 두 번째 포인트를 또 위치시키면 그것에 대한 네이버들이 또 있겠죠, 10개들이. 그러면 이 매트릭스도 바뀌고 쟤도 바뀌었으니까 얘도 또 바뀌겠죠. 또 리스퀘어로 또 풀면 되니까. 그럼 하여튼 이게 그 각각의 데이터 아이템들에 대해서 걔네들의 각각의 10개의 네이버에 대한 그 리니어 커뮤니케이션 코에피션트 이렇게 쪼르르 있으면 이게 있겠죠. 그죠? 네. 그러면 so by using this optimal linear combination coefficient we actually minimize here the assumption of the LLE is that this linear combination coefficient are preserved between the low and the high dimension space. So high dimension space vector was 1 to 5 is the center point, and then let's just assume maybe 2 nearest neighbor, maybe 2, 1, 3, and maybe negative 1, 2, 1, and their optimal coefficient is maybe 4, 5. This is a completely hypothetical. This doesn't make sense at all. I just gave the random number. So those two are the best, least square solution and their corresponding linear combination coefficient. Okay, and then these are found deterministically only using the high dimensional representation, and suppose their two-dimensional representation is maybe 3, maybe 2, 5. I'll just give a random number, maybe 3, negative 2, and maybe 1, negative 1. And suppose these are corresponding low dimensional representation. Okay, here we fix or we bring this linear combination coefficient. Okay, because that is determined from the high dimensional space, and then we assume that these linear combination coefficients are preserved. And then now those points, okay, how can we optimally determine those green parts so that this L2 norm difference or this kind of error is minimized as well. Okay, so again, those 4, 5 are computed from the least squares by just using high dimensional points. It's a center point and it's a k nearest neighbor point. Okay, and then we bring those optimal least squares coefficient into the low dimensional space as the fixed value. Okay, fixed value, and then in what kind of representation or low dimensional representations will this difference be minimized? Okay, so that is how this LLE works. Okay, so that is kind of a locally linear embedding. That's called the locally linear embedding. Why is it called locally linear embedding? Because this locally linear embedding means we embed or we represent the center point as the linear combination of the local neighbors, right? And then their corresponding point in the low dimensional space and the corresponding center point, and this linear combination relationship will be preserved. And so there's a local embedding and their correspondence, their coefficient or weight will be just preserved between a high and a low dimensional space. That way it is called a locally linear embedding. So that is an LLE, and nicely, this kind of problem, I mean, optimal kind of coefficient is also computed based on eigen decomposition from by forming some matrix. Okay, so that's another kind of that's kind of beauty of the theory behind this LLE. But in practice, this LLE doesn't work very well in many applications. So LLE is not used much in these days. But in general, this isomap kind of performs well. For example, suppose you want to perform the gender classification of a given facial image, and then you might as well just apply isomap to reduce the dimensionality of these pixel vectors into some low dimensional vectors, and then if you just train your classifier by using these low dimensional representation, which is obtained from this isomap, the performance or the accuracy on the test data or validation data may be better or improved compared to the case where we just use the pixel vectors, okay, as the input vector for the same classifier, okay, whether it is an SVM or maybe some other classifiers, okay, right? So people studied about oh my god, okay. I cannot find a good example, but so there is an image data set called Coil 20. Does anyone know about this data set? So this is you put a particular object, whether it is this laptop or iPad or something like that, and then you take a photo of it from a particular angle, and then you just rotate it with a certain degree of an angle, and then you take the photo of it, and so on, right? And then we can obtain those the same objects from a different angle, right? And then you take the photo of another object by using the same setting, right? So in that case, what is the actual variation, or what is the aspect or attribute that will create a little bit smooth variations in our data? So that is actually angle, right? But if we imagine like the teapot, this kind of teapot image in a pixel space, and this is a teapot image from another angle and so on. But if we imagine their kind of pixel space vectors, and then those pixel space vectors will not be straight, right? So they will be like smoothly moving or making some progress along some curved directions corresponding to this angle differences, right? And so we can actually map this kind of angle, which is a kind non-linearly represented or curved shaped kind of variations caused by angle in our pixel space. And if we can successfully map this angle as one of our axes, and then it will be successful kind of a result of a manifold learning, right? So here, this is a similar experiments that I did. And so suppose we have this facial images of the same person at a different angle. So this angle is quite discrete, but we can imagine these angles are kind of quite dense, and they have a smooth variations with a small amount of an angle. And then we have this angle axis that creates this meaningful kind of differences or variations of our data. And then also we suppose we took a photo on different images or different persons, and then we may have another angle or another variations caused by different person ID. Okay, and then suppose we have a multiple images in the same angle and the same person ID and so on, right? And in this case, we apply this this data set. I mean isomap. We apply the isomap into this data set, and then these are the result of the isomap, where we set a different k values, where this k is the value used in the k nearest neighbor. Okay, so here let's consider the effect of this k value in the isomap. So in the case of an isomap, if we use a small k value, small k value, and then this k nearest neighbor graph will be much coarser, or the edges will be much fewer or much sparser, right? And in that case, we want to reconstruct or approximate this kind of geodesic distance as a shortest path in our k nearest neighbor graph. But let's imagine the edges are much more much sparser than the current graph, and then this kind of shortest path will be like shortest path will be larger because we have a smaller number of edges or fewer number of edges, right? So in this case, this geodesic distance will be approximated, but it will be much noisier, right? It will involve much noise, or more exactly, it will be overestimated, right? Due to this overly sparse kind of graph representation, right? So if we can have a kind of dense edges over here, then it will be better or desirable to reconstruct this geodesic distance. But what if we use k as too large value, or too large values for our k? And then in that case, some undesirable things are happening over here. So if we set k as too large, and then those 2 points will be connected as the nearest neighbor, right? If we set k as 100, and then those 2 points will be connected as the neighbors, right? So in that case, the shortest distance will be suddenly becoming really small, right? So in this case, this distance will never be like approximation of the geodesic distance, right? So k shouldn't be too small or too large, right? So if it's too large, and then it is called a short-circuiting problem. And then if k is too small, and then it will overestimate too much. I mean, overestimate this geodesic distance due to too sparse graph, right? And so among these 3 examples, the best result or the optimal result seem to be this one, lower left one. And let's think of the the reason. Okay, so here, yeah, we can think of the two meaningful attributes that will make the variations in our data, in our pixel space, as the angle and the person ID, right? So here in this case, okay, so these are like, yeah, those points are dimension reduction result in the 2D space, and then corresponding to this cell with this angle and this guy is represented as cluster A and cluster B and so on. Okay, for a particular angle and person ID combinations, we have multiple images. Okay, and they may have a different variations depending on their illuminations and facial expressions and so on, right? But still, we can consider this multiple data items belonging to this particular cell. Okay, and then we color coded them. Right, and then here, this guy is like the x-axis and the y-axis. So x-axis is like GHI, which is found over here, DF and ABC. So yeah, in this second or this figure, the x-axis is successfully mapping mapping this angle attribute, and this y-axis, yeah, although this one is not like straight line, but yeah, approximately the y-axis or vertical axis is nicely mapping this person attributes as one of our reduced dimensions, right? So that way, this guy is kind of ideal or best result. But here in this case, ABC is curved, D is DF, and so we can see this kind of curved structure, right? And we can see this kind of warped or kind of distorted grid points over here, right? So in this case, K is set as two large values, and so it's certainly creating the short-circuiting problems. And in an extreme case, if we short-circuited every point as a neighbors over here, and then it is nothing but the PCA or MDS, right? It is just mapping the original distance. I mean, it tries to reconstruct the original distances. I mean, original Euclidean distance, not the geodesic distances. Okay, so that way we can see this kind of curved structure, and that curve is we can imagine this kind of curve is kind of projected curve from the high dimensional point to some kind of PCA directions, right? So if we perform the linear transformation or orthogonal projection onto a particular axis, and then if they are curved, and then these curve will be shown in the 2D space. So this one is showing kind of curvature in the high dimensional pixel space. Although this one is just a 2D projection example, but at least we can see that they are curved, right? And now let's look at this result where K is set as too small value. So in this case, K is too small, and it creates this overestimation of this geodesic distance. And so this overestimation is this overestimation becomes more severe when considering large distance. Okay, so in this case, let's consider the geodesic distance between these two very far points. Okay, in this case, the shortest distance, okay, I mean shortest path will have more exaggerations. But if we consider this, maybe this guy and this guy, and in this case, geodesic distance will be, I mean, it will still be overestimated, but the shortest path between these two may not have that much of an exaggeration or overestimation is not that much, right? So if we use too small value of K, and then large distance will be more exaggerated, okay? And so, so here, yeah, let's see, yeah, this small kind of K example, and then we can roughly see some kind of cluster structure. So, in this case, what are forming our cluster? ADG over here, and BEH, and so in this case, clusters are formed in this manner, right? So rather than the angle, rather than the person ID, this angle is forming our clusters, right? So we can see that, yeah, we can kind of conjecture that here, our pixel spaces, I mean, the differences caused by angle or differences caused by person ID. Which one has a larger distances? Probably the distances caused by angle will be larger than the distances caused by the person ID, and that's why, I mean, that way we probably obtain the cluster with respect to different angles. Okay, because I mean this guy and this guy and this guy, A, B, and C, are the same person, right? But with a different angle, right? So if the angle was exaggerated, I mean the distance between, I mean the larger distance was exaggerated more, and so if we see the clusters with respect to the angle, right? And in that case, the person ID, yeah, person ID will be relatively small, cause a small distance compared to the different angle, right? Any questions? Right. The next topic is TSNE, and I plan to cover details. A little bit of details about how this TSNE works, because that is probably the most popular algorithm, and also personally I did a lot of research in the past on this TSNE. So I think I'll cover details of this algorithm in the next class. Okay, that's it for today. Any questions? Okay.
K에 따라서 그 작으면 크면은
네.
뭐가 안 좋은지
크면요.
네.
크면은 기본적으로 여기서 이제 숏서키팅이라는 문제가
네.
단선이라는 뜻이거든요. 건전지에 이게 두 개의 극이 서로 연결이 되어져 있지 않고 뭔가 다른 저항이나 뭔가에 의해서 이게 연결이 간접적으로 되어 있었는데 여기가 바로 연결된다. 이게 숏서키팅 혹은 단선이라는 뜻이기 때문에 이게 이제 연결이 되면 안 되는데 이제 확 연결이 돼버린 거죠.
다 연결돼버렸죠.
네, 그러면 이게 다 연결되면 결국은 이게 나타내는 여기서 지오데식 디스턴스, 그러니까 지오데식 스페이스를 따져봐야 그게 그냥 유클리디안 디스턴스를 그냥 그거를 그냥 미믹하는 거겠죠. 그러니까 우리의 이 DH가 그냥 이제 유클리디안 디스턴스, 그냥 MDS에서 하던 그 유클리디안 디스턴스로 이 올 페어와이즈 디스턴스를 만드는 그 결과와 그렇게 차이가 없을 거라는 거죠. 그러면 그거는 결국은 이거를 구했으면 이 다음부터는 그냥 PCA랑 똑같거든요. 그러면 결국은 뭐 하여튼 우리한테 주어진 모든 디스턴스를 다 이렇게 보존하고자 하는, 그렇다면 어떤 뭐 프로젝션의 관점에서라면 어떤 방향으로 뭐 디스턴스를 가장 잘 프리저브하는 방향으로 프로젝션 했을 텐데, 그 프로젝션 했더니 뭔가 좀 약간 이렇게 좀 커브가 되어져 있잖아요. 그러니까 뭔가 이제 하이 디멘전에서 커브가 있었기 때문에 프로젝션 했을 때도 커브가 됐을 거라는 거죠.
네, 감사합니다.
네.
이번 주 수요일에 애들이랑 미팅 있잖아요.
아, 네.
그거 10시
맞아요.
10시 반부터
네네.
있는 것 같은데
네. 그 방 좀 일단 좀 예약 좀 해주고요.
근데 몇 시간 정도로 예약해야지?
12시까지만 하면 될 것 같은데요.
두세 시간 정도로.
2시간? 네, 12시까지 하면 될 것 같아요.
네.
12시부터 또 수업이 있을 수 있으니까 12시 반까지 하면 방이 예약할 수 있는 방지도 없을 수가 있으니까 12시까지 하면 될 것 같아요.
네, 그 혹시 발표 전에 이번에 준비할 거로는 이제 그 뎁스 에스티메이션이랑
네.
셀리언시 디텍션 각각 좀 학습 방법이랑 데이터 세트
네.
이 정도면 될까요?
그리고 우리가 뭘로 할지, 그러니까
어떤
우리의 초이스는 뭔가.
제가
네.
찾은 게 있는데
네.